Well, Luke, welcome to 2019.
Yeah.
And we're back again. So it's time to get our discussions of cosmology back on the road.
Yep, let's go.
Okay, so I thought what we'd do this week and possibly for the next couple of weeks is we'll deal with a few of the viewer questions we've had posted in the comments below. So people feel free to post their questions and we'll try them. So this week our question is going to be...
Well, let me just read it off the teleprompter. So we've been asked, doesn't the fact that we know there is a finite age to the universe dismiss the claim that it is infinite in size? How could you shrink an infinite size to a singularity? So the question there is, if the universe is a finite age, how can it be infinitely big if it started at a point?
That's an excellent question, but can I start off by saying is that you've got a future in BBC sort of panel shows. Your teleprompter reading was excellent.
Oh, very good.
Okay, so let's pick this question apart. Okay, so what we know about the universe comes from our observations of the universe, and what we have seen over the last few years is our universe is filled with this dark matter and dark energy, and one of the things we've been able to do is measure the shape of the universe. And of course, this has been one of the big questions people have had since modern cosmology, almost 100 years ago it was born. What shape is the universe? And as you know, there are three kinds of shapes the universe can be. So do you want to run through them? Okay,
so this comes around actually just from mathematics. You just ask yourself, okay, what sort of three-dimensional shape could we draw? In this case, it's really kind of, if you're thinking like of a sphere as a three-dimensional shape, it's really kind of a four-dimensional shape, but never mind. So it could be perfectly flat, like our universe, where what we mean by that is that the ordinary laws of Euclid, ordinary high school geometry applies. If you draw a great big triangle with three straight lines, the interior angles will add up to 180 degrees. But those aren't the only options. You could also have a universe which is positively curved, like the surface of the Earth is, for example. If you walk in straight lines around the Earth, and you walk in three straight lines that join up to each other and then measure the angles, if you draw out a big enough triangle like that on the surface of the Earth, you'll notice that the internal angles are actually more than 180 degrees. That's one way you could work out that you are, in fact, on the surface of a sphere. If you walked around, a little ant walked around a saddle, made a little triangle, the internal angles would be less than 180 degrees. Okay. So applying that to the universe as a whole, those are the three options of from Einstein's theory of gravity, what space could be like.
Okay, and so what we have from those pictures, of course, is that we have those three shapes, and they imply, in a way of thinking about this, that there's possible volumes to the universe. Because as you mentioned, the positively curved shape is like the surface of the Earth. The surface of the Earth is a finite amount. And so if the universe was positively curved, it would be a finite volume, a volume that's growing over time, but a finite volume. The other two shapes, so the flat universe and the saddle sort of shape universe, they imply a universe that spatially goes on forever.
Certainly the simplest way to make that geometry is to have it go on forever.
Yes, and we're going to be very careful here because we may have some mathematicians listening, and they might know that Einstein's general theory of relativity is a geometric theory, but not a topological theory.
Yes.
Right? So this is where things get a bit murky because you can have flat surfaces which are not necessarily flat like a piece of paper. And the well-known example, of course, is the tube or the torus.
Right. So what you can do is you take a flat surface, but then you make it like Pac-Man. So if you go off one end of the flat piece of paper, you come in the other end. So topologically what you're doing is curving the space around, and then you can curve it around the other way, and you've got a completely closed surface. You can't walk off it. Okay, so it's got a finite area, but it maintains its flat geometry. If a little ant walked around, doesn't quite work for an actual torus, but if you sort of put together a space like this and a little ant walked around, they would see that the internal angles of their triangles add up to 180 degrees.
Okay, but we'll stick with the simplest idea here that these universes, the flat and the saddle shape one, the hyperbolic one, they are infinite in extent. So spatially they're infinite. And what we've learned from our observations is that the curvature of our universe appears to be flat, right? It shows that the universe appears to be more like a piece of paper, a flat piece of paper, than it does a saddle.
Yeah.
Which would imply that our universe is infinite in extent, right? So spatially infinite.
The simplest case.
The simplest case. So how does this fit into this picture of the Big Bang singularity? So this is of course, the word singularity itself comes with a bit of mysticism attached to it, right? But as a physicist, what does singularity mean to you?
What does it mean to me?
Yeah.
So a singularity in Einstein's theory of gravity is just that there are certain points in space-time which don't act in a sort of normal and nice way. So when you start when a mathematician starts piecing together Einstein's theory, the most important thing about it is that locally, if we look really closely at a small bit of space-time, it should look basically flat. Right? So the Earth looks basically flat if you look at a small enough bit. All the curvature is sort of a large scale things. But that's important because you want it to be nice and smooth, because as long as it's nice and smooth, then everything's kind of normal at a lower level, at the bottom level. So, technically, you want to be able to do calculus. You want to be able to put down, curves and stuff like that. Anyway, those are the details. For a singularity, that falls apart. And so the question was always, okay, we can actually sort of construct these space-times which have weird points in them where it looks like something really odd is going on. So, for example, the density becomes infinite. So there's ones at the middle of black holes, and something weird's going on there.
Yeah.
Where and the other obvious one is the Big Bang, of course, within the classical model. The question was, these were always sort of weirdo things in general relativity. And then it was really in the 60s and 70s when Stephen Hawking and Roger Penrose proved that actually these things were kind of unavoidable. They weren't just pathological weird cases.
Yeah.
They turned up in a whole lot of space-times. Smooth structure of space-time breaks down and it becomes basically a boundary to space-time in some sense.
And I think there's a subtlety here. You used the word point several times.
Yeah.
But we're not only talking about a point in space. A singularity can be a point in time.
Yeah.
Right? So this is the issue with the Big Bang, is that it is singular. And what we have is that as we wind the clock of the universe backwards, it gets denser and denser and denser. Things get closer and closer together. And when we hit the Big Bang, the density goes to infinity, explodes, becomes undefined. And we hit that singularity. Okay? But that's a point in time. Right? We've gone backwards. So the question is, the universe is infinite today. So how big was the universe yesterday?
It was infinite.
Infinite. How big was the universe a billion years ago?
Infinite, yeah.
Okay? And if you keep winding the clock back, every time you ask the question, how big is the universe? The answer comes back as, it's infinite. Right? So at that moment of the Big Bang, right, the universe was still spatially infinite. So we never had a period of time where we went from having a finite universe to an infinite universe. It's always been infinite. And the way to think about this properly is that the singularity is the divergence in the density which occurred everywhere in this infinite amount of space at the birth of the universe. The universe was born infinite. Yeah. It is infinite, and it will be infinite into the future.
So you're right to point out the problem with the point, right?
Yes.
So if you have a picture of this point which is just sitting there and then the universe explodes out of it, then how on earth do you get an infinite universe if you just started with a point? But that's not the kind of, as you point out, too many puns there.
Yeah.
That's not the kind of point that a singularity is.
Yes.
It's a boundary on the edge of space-time. It's not really part of the space-time itself. Mathematically, what's happening as you approach that is you have an infinitely large universe and you have a scale factor, which is how big it is. And so the size of the universe is which is infinite, is being multiplied by a number with the scale, which is now approaching zero.
Yeah.
And so the singularity is precisely the point at which those two things collide with each other, and we don't really have a point in the space-time.
But we should also point out there's an important caveat here, right? Everything we've spoken about comes from the equations of general relativity. And we know that in this early phase of the universe where it was extremely dense and extremely hot, gravity was the dominant force on the expansion of the universe, but we also know that quantum mechanical forces must have been playing their part as well. And without this grand unified theory that everyone's looking for, where gravity and the other forces play nicely together, we don't really know what happened in those initial sort of instances of the universe. So what it could be is that the singularity that we see in Einstein's equations is basically telling us is that we don't understand this region. this time in the universe. And it could be that when we eventually have our breakthrough, fingers crossed, and we understand gravity and the other forces a bit better, the singular nature of the birth of the universe might not actually exist.
Right, so let's sum up. So I think the short story here is the universe is not infinitely large because it started at a point and then expanded really quickly. If the universe is infinitely large, and we don't know, but probably, even probably is a bit too much. If the universe is infinitely large, it's always been infinitely large. The expansion still makes sense because you can make more space between any two galaxies. But it's not the case that the universe starts as a point and then expands really quickly and makes it to infinity.
Absolutely. That's a really good point to finish on.